Hello, so today we're going to indulge in some mathematical theory, and I want you, regardless of your mathematical background, to bear with me and just kind of watch this process, because if you're going to really understand analysis of variance, it's important that you grapple with the theory and understand its underlying basis. So that's what we're going to spend time on today. And to get you really focused on it, I'm going to actually blank out my smiling face here and just talk to you about this a la Khan Academy. In other words, just with a sketchbook. And so that I give myself maximum space to actually talk about the theory and to show you the equations that are involved. So we're talking about the theory of the F test, and I've given you sort of the background that the ANOVA is going to produce an F value associated with an effect in our model, and the F value is actually going to be a ratio. So a ratio of variances. And I've even given you the hint that the ratio is going to contain in the numerator variance due to groups being members of a particular group plus variance that's due to being due to within group variation, and then the denominator is only going to carry the within group variation. And so what we're really testing here is whether this ratio is inflated above the expectation for two variances, put this in quotes, two variances that are actually drawn from the same parametric population. In other words, does the identity of being within a particular group add to the variance significantly? And so we need to actually construct this variance, this ratio, by understanding these variances. So, let's imagine that we have we're going to keep this generic here in our theory. So we have A groups. Now A could take on the value of, A could be 2, 3, 4, etc. We could have however many groups we want here. So we're going to construct a general theory. Then within one group, we already know the formula for variance, right? Can you write that? Sure you can. It's going to be the summation over all the individuals within the group of Yij. And by the way, this I refers to the group, and we're just talking about one group at this point, so it might be group A, for example, or group, males, or whatever our groups happen to be. And this is the individual J, and we're subtracting from the mean for that group, and we're taking the square of that, and we know it's a within group variance, so we're going to divide by n-1 to correct for small sample size, because we're not measuring the entire group, we're measuring a sample. And so this is within one group, so the average within groups variance we would find, just as we typically do for any average, we would sum across all I groups from 1 to A, and we would sum these variances that we've just created here within groups and divide by n-1. But this isn't the average, right? This is just the sum. This is the numerator. And we would divide by A because we have A groups, because this is an average. So we're taking the average variance by summing across groups and dividing by the number of groups. So think about that. That's how we construct any average, right? If we want any y bar, we take the sum across the components and we divide by the number, right? So, you know, we're not talking about an average of observations here. We're talking about an average of variances, and we're going to divide by the number of groups contributing to that. So with the average within groups variance is given by this formula. So what is that giving us? That is giving us this phenomenon. So what we've constructed here so far is the denominator of our f-test. We've got the average within groups variance, and now what we need to do is figure out the numerator. Okay, so part one, we started with the denominator of this f-test and we figured out the average within groups variance, and here's our formula for it. Okay, so keep that down in your mind. All right, so next we're going to construct the variance among means. Or let's see, so just going to slow down here a little bit. Okay, so we're going to get the variance among means. All right, so let's erase this here. So we're going to get our numerator. Oops, our numerator. And we're going to construct a variance among means. Now this is not actually our numerator yet, but we can see that the variance among means is going to be the group means minus the grand mean, the mean of all means, squared, divided by, how many groups do we have? We have A groups minus 1. So this should look to you like a variance, but it's a variance among means. So the formula is exactly like any variance formula, except that we're looking at the deviations of the means from the grand means, the grand mean of all the means. Okay? But the variance of groups is actually, the way maybe to think about it is the variance among means is the variance of groups divided by n. So the variance among means is smaller because we're taking an average, so we've lost some of our total variation, and to get it back, to get the variance among groups, we would actually multiply n times the variance among means. Okay, so that takes some thinking about, and if you want to kind of go back to the root of this concept, take a look at Sokol and Rolf. They explain it in more detail there. But basically the idea is that when you take a mean and look at the variance among means, you're averaging across your observations, so you're obviously going to eliminate that variation, and so to get the variance among means, we actually divide the group variance by n. Okay, so now we have the variance among means, and so the variance among groups, using that formula, is going to be n over a minus 1 times y sub I bar minus y double bar quantity squared. Okay, so the variance among groups, and that just comes from this, so we have the variance among means, but we're multiplying by n. All right, so remember this. This is going to be our numerator. And we already have our denominator, so let's now put them together and construct our f. So f equals a rather massive, ugly-looking quantity, n over a minus 1 times the summation of yi bar minus y double bar, quantity squared, oops, there we go, all divided by 1 over a times n minus 1 times the summation of I from 1 to a times the summation of j from 1 to n, all over yij minus y bar I quantity squared. Okay, woohoo. We are excited. We have an F test. Now, what we haven't really done is understood how this is going to logically tell us that only the numerator contains variation among groups. I mean, you can kind of get it because we based this on the means, but the denominator was just an average of the within group variance, so this obviously doesn't seem to contain that, but this does seem to contain it. But we can actually do a little bit more theory about this that shows it more explicitly. So I introduced in a previous video our statistical model, why our observation is consisting of an effect that is due to being a member of group I. So this is the the treatment or the sex of the individual or some other aspect, some nominal characteristic of that individual that we have many of, so we'd have replication, and then this is our error variance above that. So I already introduced this in a previous video. So let's imagine now that we know our observations up here, our y sub I, have these effects in them. Okay, so what we're going to do is we're going to alter these y sub I by adding in an alpha effect. All right, let's break it down and do it one step at a time. We'll do first the denominator, and then we'll add alpha into the numerator. Okay, so let's start over with that. So you've got that down, right? Okay, so let's start with the denominator. Here we are, the denominator of our F test. There we go. And we have the summation over I, the summation over j of y ij. But now we have alpha added in. The alpha due to being a member of group I minus y bar I, and obviously the average effect of being a member of group I is added into that average as well, right? And then all of that is squared all over a times n minus 1. And then we can simplify that a little bit, rearranging terms, summation of I, summation of j. Let's rearrange yij minus y I plus alpha I minus alpha I, look at that, all squared over a times n minus 1. This is looking good. So what happens here? This is 0, right? So alpha drops out, and in the denominator, our treatment effect is gone. And we simply have our average within groups variance. So alpha is not in the denominator, so our treatment effect is not there. And remember, back to our original thing, we wanted a numerator that contains the treatment effect, or the alpha effect, plus the within groups, and in the denominator we only want the within. So we've checked the denominator, check, we're there for the denominator, but we need to check the numerator as well. So let's take care of that for the numerator. Now our y sub I bar is now y sub I bar plus alpha sub I. Okay, so when we go to the numerator, we're going to also have to consider that for the y double bar. We're going to have it's going to be the summation I from 1 to a of y bar I plus alpha I. All right. And we're going to divide by a, right? For that's the grand mean of means. So we have 1 over a times the summation of y sub I bar plus 1 over a times the summation of alpha sub I. So one way you can think about this is that's alpha bar. It's the mean effect of treatment, alpha, whatever we're talking about here. So y double bar equals y double bar plus alpha bar now. Okay, so that's, we'll substitute that in our numerator. All right, so now I think we're ready to jump ahead and look at our numerator formula. And let me see, yeah, I think I need to delete this and start at the top. So our among groups variance, look back at our formula here. We're going to now substitute our new values for y bar and y double bar. All right, so we have n over a minus 1 times the summation of y bar I plus alpha I, right, minus y double bar plus alpha bar quantity squared. And we can again rearrange terms, equals n over a minus 1 times the summation of y bar I minus y double bar plus alpha I minus alpha bar. Notice these don't actually turn into a 0 here, do they? Okay, unlike the last time. So now what we have is a plus b quantity squared. So you might want to recall the binomial expansion. A plus b quantity squared equals what? A squared plus 2ab plus b squared. So we're going to do the same thing as that with this. So we're going to have this equal to n over a minus 1 all times some huge thing here, which is going to be basically the binomial expansion of this up here. Okay, so we have, first of all, y bar I minus y double bar, that's our a, squared. Then we have I need to keep my summation signs here. So we're going to have then yi bar minus y double bar times alpha I minus alpha bar all times 2 plus summation of alpha sub I minus alpha bar quantity squared. Now, and I put the close brackets here. I could distribute this among all of these, right? I could put that there, there, and there. I'll just go ahead and let you do that if you would like. But let's look at this first term. When multiplied by n over a minus 1, what does that give us? That is the variance among means not due to treatment. Right? Because we will naturally get a variance from the grand mean of any particular sample. Any group will vary from the grand mean just by chance because of a small n. It's not perfectly representative, and so we know that there is a variance among means that's not due to the fact that they are from different treatment groups alpha. All right, now let's go over to this one. I'm going to skip the middle one for a second and talk about this one. So this is the added variance component due to being a member of a particular group. Okay, so there'll be some average treatment value, alpha bar, but this is the deviation due to being a member of a particular group. So let's imagine just real briefly, this alpha bar is the mean for males and females, and alpha I might be the mean for females, and there will be some deviation due to that, and then alpha I equals 2, I equals 1 would be females, I equals 2 would be males, and we'll get a variance due to being a member of each of those groups. And that is in this quantity up here. Okay? So that's good. That means that we have appropriately included that. The puzzling one is this one. And you might think, oh my gosh, this adds a real complication here because we do have deviations from grand means of means, and we have deviations of groups from that. So you might think, oh gosh, we have an added component here. What are we doing with that? Except that we would expect no correlation between these values, right? This is just a random deviation of being a member of group I from a grand mean. And then this is the deviation of being a member of a particular group from the group mean. There would be no expected correlation between these. In other words, positive values and negative values cancel out because there's no covariation. That's actually what this is. This is a covariation between these quantities, these deviations, let's put it that way, okay? So the expected value of that term on average equals 0. So this term falls out, leaving behind only this variance among means not due to treatment and the added variance that is in fact due to treatment. All right. Now, what we're going to do actually in class, and if you're not in my class, I recommend you try this. Create a data set where you actually add a variance component and show that this actually is true. So in other words, create a data set where you have created multiple groups. Keep it simple. I recommend a KISS data set for this. Keep it very simple and show to your own satisfaction that the added variation due to being a member of a particular group that you have put into that data set shows up in the numerator but does not show up in the denominator. And then I think once you do that, you'll be really satisfied that you have a deep understanding of analysis of variance. Okay, so here's the underlying theory. I realize it's a little bit complicated, and it really relies all on our basic idea that any particular observation, y sub I, is determined by being a member of a particular species, for example, so that has a certain mean, but also by being a member of a particular group, and then also the individual variation above and beyond that group variation. Okay, so you can kind of, again, going back to basic components, think of any particular observation as being a sum of some group effect and some error variation. And it could be any combination. Now, the interesting thing about this is that so we only observe this. We don't, and it almost seems like kind of magic that we can then take a population of these observations and we can determine this thing. We can't really determine it exactly. We can just estimate it. And then we can see, using residuals, what that is. So it's kind of cool. I mean, what statistics is really doing is breaking down this number into components that are explanatory. And if you start thinking about observations that way, as being comprised of underlying effects and random variation, I think you'll start looking at the whole world a little bit differently. But here it is in simplified mathematics, and you can imagine that when we have multiple alphas and we have interacting effects, the mathematics is more complicated. But this is the simplest mathematics presentation of a simple one-way, one-factor added analysis of variance. Okay, guys, you may have to watch this a couple times. Talk to you later.